start your presentation, Austin.
Yeah, thank you. I really appreciate. I actually want to take the time real quick to thank Scott for having me. I think this is a great opportunity for a lot of people to kind of figure out the different works of their HVAC system and kind of see whether they're losing efficiencies. So there's a lot of different aspects of your HVAC system. So you have motors, you have your fans, you have the different aspects of how your airflow moves through the system. And then there's also different effects that affect the efficiencies on the miners themselves. So if you can dissipate the heat sinks, the heat off the heat sinks on your miners more effectively with your HVAC system, what that's going to do long term is it's going to make your miner is going to have it's going to perform better for longer periods of time because it's not stressing out the internal components of the miner itself. And then you also have these different factors where the environment around your Bitcoin miner, for example, like different air densities, different pressures, different works in your HVAC system that actually cause back pressure to go back into your miners and cause issues where you're cycling your own heat from your miner. Different vacuums, different measuring tools, and then also like mistakes that people make that I see very often in the HVAC industry for Bitcoin mining is I've seen a lot of HVAC engineers that they do industrial, they do commercial, and they do residential, and they try to calculate this and approach this the same scenario with Bitcoin mining like they do for their industry, and it does not relate because the way that we operate is on such a large scale. You're talking about one Bitcoin miner a year is going to move 210 million cubic feet of air. If you think about that, that is a massive amount of air, and then you put that on a scale times 10 times 100. And then these people that are up in the scale, and that's what you're trading off because you have you use a lot of energy for your Bitcoin miner and you use a lot of air. So those are the two things that you really want to simplify so that you can have an higher ROI and you can increase the profitability for your Bitcoin miner. So what we're going to do is we're going to start breaking into some of these items, and then I'm going to talk about a couple of the subjects.
Awesome. Yeah. But,
to start going.
First, yeah, I just want to welcome again everybody that's on this webinar. Typically, these monthly webinars are technical deep dives on very specific issues relating to Bitcoin mine operations, and either how to build a mine or how to operate a mine more efficiently. And yeah, again, we're just really grateful to have Austin here this morning talking about HVAC and how to save money operationally and also on a CapEx perspective as well. Yeah, so before Austin goes to the next slides, which I'm really looking forward to, I just want to have Trevor jump in quickly. Trevor is a new student of ours, and we've just been having a great time hanging out. So just, yeah, why don't you unmute yourself, Trevor, and, just tell everybody what you're most looking forward to today on this call.
Hey, guys. There's this phrase that I've heard a lot from a lot of people. It's you don't know what you don't know. And as a Bitcoiner, I know a lot of things about Bitcoin, but I don't know a whole lot about mining. And so when it comes to HVAC, I had no idea that that was something that you had to deal with and take into account when building out a Bitcoin mine. So I think that's what I'm most excited about today, is just to learn the things that I don't know. So I really appreciate you, Austin, and you, Scott, for facilitating this and giving us the opportunity to learn what we don't know.
Absolutely. Cool. All right, Austin, back to you.
Yep. Much appreciated. So before I get into like the depths of all the different subjects we're going to be talking about, I actually want to introduce myself a little bit and kind of build a little bit of credibility in my background of work. So I actually chose an architecture route. I went to Ball State and Purdue Fort Wayne. I then eventually was hired by a custom home builder as a architect, and I did about 8 to 13 homes during that time period of different floor plans, and then they got developed. And then prior to that, I actually had previous experience with thermodynamics. So when I was a little bit interested into the crypto mining, but I just didn't have the capital and the central knowledge to kind of, well, electrical knowledge was kind of the capacity for me. So then what I did was I quit my job as an architect, and I kind of took on the full on scale build. So what I did was we got a warehouse, it was roughly about 40,000 square feet, and we started building out this 3 megawatt mine. And during that process, it was a headache of problems where we had problems where we were hiring HVAC engineers that were miscalculating the actual CFM that was being outputted of the fans. We had problems where the electricians, they weren't cooling down the lines themselves, so then the lines were tripping. Because if your terminals on your, if anybody knows about electrical, if your terminals on where your connections are, if they are not grounded right, or if there's a weak connection and then it starts getting hot and you have vibrations, which is almost inevitable with Bitcoin miners because they emit sound, and sound is vibration itself. So there's all kinds of different liabilities and different aspects and risk factors that come along with trying to engineer these systems. And trust me, I have had a ordeal of my own trying to figure all this stuff out. But when you start taking it to a scientific standpoint, that's where you start seeing the results. And those are the results that you want, because you can test those results and then you can test them again to see if you get the same result. And the way to get a confirmed solid variable, I call it a control variable. So you have a control variable, and that is a standard variable to go off of. Well, how do you find those control variables? And that's what we're going to be going through today. Is there's actually certain organizations that that create standards for these control variables. So for like electrical efficiencies, you have organizations like NEMA, or International Efficiency Codes, and they'll specify the standards for each classification of energy efficiencies. And this is actually standardized because energy efficiency is kind of on everybody's minds in the industrial industry, because if you put a 1 amp of power out for 24 hours times 365, it slowly turns into kind of like an exponential scale, where you're not paying 6 cents for that day. You end up paying 6 cents times 365, or 6 cents times 24 times 365. So that's where the math can get lost in translation, and you can get burned really quickly in your financial endeavors trying to organize these systems. And that's what we're kind of weave in and out today. And then you're also going to see where I see people get burned most too is the fake specs too. Is you need to avoid the fake specs, because there is a lot of dishonesty in this industry, and there's a lot of people who they can say they can sell you something, and they know that you can't test it, or you can't uh, mitigate their claims that it's not performing to that certain aspect, because you don't have the measuring tools like I do, or like certain static pressure sensors, or you have different tubes and whatnot to test the different velocities of the fan, the certain resistances that it can handle. Because you can have a guy come in and say that this fan does really good, and he can sell you that fan. It might work good for his application, but if you put it in your application and you have something completely different than what he has environmentally wise, it's not going to work the same for you as it did him. So that's what we're going to try to figure out, and kind of help you guys with that, and then kind of see the different aspects of how do I gain a higher ROI through taking these different avenues, and how do I reduce my risk from the long-term financial endeavors. So through this, we're going to kind of like, we're going to see the difference between belt drive and direct drive. I feel like that is one of the biggest misconceptions in this industry, is people they optimize for direct drive because they see the maintenance advantages. There's less greasing, they're pretty much maintenanceless. if that makes sense. But the overall goal is actually not just maintenance, it's the efficiency. Direct drive is not efficient. I can tell you that it's about a quarter to half efficient from belt drive, but there are certain engineering obstacles in the way that make belt drive harder or undesirable. And there are certain ways to fix that, and that's what we're going to start getting digging into as well. So to the thing I want to kind of focus on is actually the credibility aspects. So with motors today, they're evolving. So you have motors from 1960, they're extremely inefficient. Then it was up until like 1992, there was an E-Pact motor that came out. It was the first ever motor to create NEMA efficiencies and surpass the 90%. And then since then, there has been titanium motors. There have been FASR motors, which are ferrite assisted synchronized reluctant motors, a giant word. Then you have different types of engineering in the motors that actually cool. They run cooler so that they can handle the stress that comes with the heat in the Bitcoin mining systems. So what this is all going to relate to is long-term reliability, long-term efficiency, and the max ROI gain. If you have a fan, this is actually the most common problem I see, is people buy fans and they last about 6 months to 18 months, or they might get lucky and get 2 years out of their fans. But in the process of that, you're doing a 2-year ROI, and those fans over time are losing their efficiency. If your fan is dying in 2 years, that means that progressively every year your half of the efficiency of your fan is losing because your bearings are essentially grinding. So if you think about a circle, right? If the circle is completely diameter, right? And then if your bearings are square, it's almost impossible to efficiently roll them around, stuff like that. So it's almost like a car. The example is almost like a car on square tires opposed to a car on circle tires, because that's what happens when your fans start destroying themselves from the static and dynamic resistances in your system. So this is what we're gonna weave in and out, and then I'm just gonna start with this video that's gonna start explaining the different efficiencies and kind of explain how this is all optimized in a certain aspect. But to begin, I would like to kind of lay out the foundations of what your basic goals are for Bitcoin mining. So if you're running smaller scale, let's say you're doing like 1, 2, 3, 4, 5 residential, you're not going to be playing much of a game of how much air can I be moving, because you're going to either have a small HVAC system or you're going to have a vacuum HVAC system that's either heating your house or something that's being cycled back into the energy, or it's offsetting your costs essentially long term. So what we're going to get into is the how the basics. So how are you going to approach this? If I'm doing 6 Bitcoin miners, how am I going to start this? How am I going to, what was the first thing I should start thinking about when approaching an HVAC system? So you're going to want to look at the output CFM. So each Bitcoin miner is going to be variable. So some Bitcoin miners move more air than others, and it's kind of hard to gauge. You can actually ask me after if you have any questions about a certain Bitcoin miner that you have. I have noticed that some of the Watts miners, I don't know why, but they run extremely hot and they also use a lot more air. I think it's just because of the fan design itself and the static resistances from the fan. But the overall goal for Bitcoin miners, you want to pull. On your hash boards, there's a heat sink. So this is connected to all the different chains, and it's pretty much the part that gets really, really hot in your system, all your Bitcoin miner. So what you want to do is you want to cool down that heat sink as much as possible, because that's what's going to dissipate the heat from your miner in terms of hash rate. So if you can dissipate that heat faster off that heat sink, then what you're going to do is you're going to increase the efficiencies of your Bitcoin miner. So your Bitcoin miner can then increase the energy that it's using, increase the hash rate that it's using, and it can be more profitable in that sense. And this is where I see a lot of people go wrong, is they just rely on the Bitcoin miner itself, its fans itself, to cool it. Well, those fans are not really designed to effectively dissipate the Bitcoin miner heat, unless you're doing something smaller scale, because you have certain things where you have a giant vacuum that can eventually wrap around back into the Bitcoin miner. And that's really what you want to avoid. And that's why we're going to get into the architectural aspects of it too. But before I get into all of this stuff, we're just gonna hop right into this video. But before we hop into the video, I want to show you guys, well, actually explain to you guys the different things you should be looking out for in this video. So you want to look for different new technologies that are being innovated, how they're different from the older technologies, and then how it's more energy efficient, how it's going to save you more money. Because in this video, it'll actually tell you that you're going to save 40 to 60% energy just by optimizing for a variable drive, which is going to be it's going to use a capacitor to take your DC voltage and relay it into an AC voltage. And I could sit here and explain it, but it's so much technical information that you're going to get lost in translation. So the best way to do it is kind of just have a 3D diagram and somebody explaining it for me in a better, more clear sense. So I'll start with this.
Older motors are less efficient than modern motors available today. Most older motors operate direct online, or DOL. These three-phase AC motors control speed and torque through mechanical means such as gears and brakes, and control flow and pressure.
So you're probably wondering why I'm showing you an example of a pump. Well, the difference between a pump and a HVAC system is actually not that much different. The way that an HVAC system is actually gauged in terms of water. So when you look at a HVAC system, in order to look at the resistances in a system, you have to look at water, because the way that the air, it's moving so fast in our system that it literally moves like a hard material, if that makes sense. It's almost like if I take a hose like this, for example, if I take this and I blow air through it, it's going to, with a smaller hose, it's going to create resistance inside this tube, but then exhaust it out here. Now, what's happening in a Bitcoin mining system, and I see this is the biggest problem, is that in this tube, there is so much pressure on the back end of this that it's almost like a balloon. So instead of having a tube with passive air flowing through it, your systems are almost like a balloon where this is closed off. And if I put pressure through this, that pressure wants to come back into me, and it gets exerted on the sides of this tube. So that's kind of a good way, or a different analogy to look at this. And then this is actually going to break down into the different technologies and whatnot that I described about.
With valves, dampers, and throttles. If these motors are not operating at 100% capacity, energy is wasted. Today, energy management is on everyone's mind. We want to use only the energy that is required for the system, nothing more, nothing less. There's a shift in today's motor systems, and that's moving from DOL to variable speed operation with an inverter duty motor, paired with a variable frequency drive, or VFD. VFDs control the frequency and voltage of the electricity that's fed to the motor and the equipment it powers. By removing the mechanical means of speed control, a motor system controlled by a drive uses 40 to 60% less energy. However, certain issues are presented when energy is controlled through a drive versus directly.
Okay, so before they showed that there was a problem with older motors, and then the solution was optimizing for a variable frequency drive because it saves you 40 to 60% energy. So that is the foundation point. But it sounds really good in light and all that. But if you look at the obstacles and the different variables that come with a VFD, there are tons. You can actually run into more problems than you would not running one. And that's because of the way that the energy is fed through the line. So that's why you have to be very careful. There are certain things you have to put in place, like EMC filters, EDM, grounding brushes. There's a plethora of different, I call them insurance factors, so that you can protect your system and you're not destroying it. So the other thing that you also have to be careful of is if you're going to optimize for a variable frequency drive, they're almost like PDUs, where if you have a PDU that gets way too hot, or if its ambient temp rises past its operating condition, well, rating operated conditions, you'll see these explosions, arcs. I've actually seen these very frequently with the Raptor PDUs. But another story. So that's what you want to be careful about, is if you're going to try to attempt to use that, get that 40 to 60% energy gain, you have to be very careful about the infrastructure that you use and put in place, because it can quite literally blow up and become a liability for your company or whatever you're running. But I do highly recommend using one. That way, like they said, you can use the required energy for the system, nothing more, nothing less. And I think that's probably the best line in this video, is to describe what you're trying to achieve here. Is you want to use nothing more, nothing less. You want to have it completely optimized for the absolute most duties that your Bitcoin miner can handle. That way you get the most ROI out of your Bitcoin miner, and you get the most out of your HVAC system, and you know you're not just burning up money every second or every kilowatt hour. But I'll continue on this, and this will kind of break down
Hey,
the
Austin,
power aspect. Yeah.
before you continue, I'd like everybody to go to the activities section of this Google Meet. It's in like the bottom right-hand corner. It's like three little things: a triangle, a circle, and a square. There's a poll in there. If you guys see that, just go ahead and answer that poll. I want to see a few more votes on there. The question is, have you already purchased an industrial exhaust fan or a mobile mining container that has fans on it? I see 4 people have voted so far, yes or no. 5 people. So, yeah, if you're having issues finding that, just look at your screen right now in the Google Meets, bottom right-hand corner. There's an activities section. Click that and scroll up to polls, and then answer that. All right, cool. Thank you, Austin. Go ahead.
Thank you. So yeah, this is this next segment is going to show the way that the energy is converted. So instead of me trying to paint the image of how a three-phase works and the frequencies and the lines, because frequencies almost work like a waveform. So the way that I'm going to do this is just kind of show you this general representation. You might not get it, but it'll at least give you kind of a highlight on how it works and how it operates, and how the different aspects. It'll actually lay out the foundation of a very common problem I see in motors. So there is a very common problem in motors where people don't have grounding brushes in their motors, and their motors are actually discharging electricity, just dumping electricity into their fan housing itself. But before I get too deep into that, I'll have them explain it a little bit.
DOL three-phase motor, the sine wave is perfectly balanced between the three waves in frequency, phase, and amplitude, and the sum of the three phases always equals 0 volts. When we introduce a VFD to control the energy fed to the motor, the energy from the power source goes through a rectifier, which converts it to DC power. The DC power is then fed into a capacitor inside the drive to smooth the electrical waveform to provide a clean power supply to the next step. Power then flows through the capacitor to an inverter that changes the DC power to the output AC power that goes to the motor. This step allows the drive to adjust the frequency and voltage applied to the motor based on the equipment operating demands. When motors are controlled by a VFD, the power is converted to a series of high-frequency pulses that emulate the approximate sine wave, but is not exact with high harmonics. The result is an imbalance known as common mode voltage. Common mode voltage builds up across the bearings due to the dielectric effect on the bearing grease and will eventually discharge through the bearings in what is referred to as EDM, or electrical discharge machining. Over time, this continual arcing will cause damage to the surface of the bearing race, resulting in vibration and heat, loud operating noises, and eventually motor failure. Using proper VFD cables and bearing protection will help.
Okay, so that section is actually a really good section. So how I talked about, I used the analogy of a pretty much like a car on square wheels. So that analogy actually applies into that exact example. So what you have is you have people, they're using, they know that the VFDs are going to bring them more energy, right? So then they optimize for them, but they have no idea about the different obstacles that come with that. There's all kinds of different electrical paths that your motor can discharge through the bearings, through the shaft itself. And that's that perfect example of how when you do that, that it literally goes in there's a discharge literally going into your fan. And that's just waste energy. That's doing nothing. It's not going into your HVAC system. It's just being dumped. And if you're dumping energy that's doing nothing, it's hurting your ROI. You could be spending that money towards other infrastructure or growing your capacity, or, there's just a lot of things that you can do otherwise with that money. And that's why efficiencies are so important, because you can cut costs on operating so that you can improve your long-term ROI, because that's the game that you want to play when you're especially up to capacity, is you don't want to spend $50,000 a year to run a megawatt and only make about $70,000 profit or something like that. That's just out of number variable example, but those are the different paths that you want to take so that you don't get burned, and you also don't want to discharge that energy because it ruins your motor and your bearings too. So when you ruin your bearings, you're just you hear these loud noises, your motor fails, and you're putting a lot of stress on everything that's inside your system. So that's the number one thing you want to avoid. And I see a lot of fan companies go extremely cheap on bearings just because I don't know why they do that, because bearings are not that expensive. I mean, talking about like $300-$500 for premium bearings compared to $100 for non-premium bearings. So you might pay 200x on that, but you're going to get 10x life on it. So be very careful on the internal components too. And the other thing to note is on the bottom it says not all motors controlled by drives will experience EDM for this scenario. The reason for that is because there actually, like I said, there is certain variables that you can put in place. There's certain grounding brushes, but there's different trade-offs, and that's what it's going to get into, is the different solutions, how older solutions, they provide a somewhat solution, but they're not the best choice. And that's what we're going to kind of weave in and out, is kind of what's the best choices, what are the more modern choices, and how that's engineered, and the advantages that come with that too. So
help protect the life of your motor and driven equipment. Bearing protection from shaft currents can be done in a couple of ways. Shaft grounding brushes, similar to the carbon brushes used on DC motor commutators, have been in use for more than 100 years. Brushes provide a low impedance path from the rotor to ground so that the shaft voltage does not build up to the point where it discharges through the bearings. However, the brushes are subject to wear because of their contact with the shaft and will eventually need to be replaced. Bearing protection rings also mitigate shaft current issues. They use multiple strands of electrically conductive fibers arranged inside a ring that goes around the shaft. They can be mounted internally or externally to the inverter duty motor. The ring remains stationary while the brushes ride on the surface of the rotating motor shaft, directing the current through the brushes and safely to ground. As with grounding brushes, protection rings will need to be replaced as they wear out. Bearings made from an insulated, non-conducting material such as ceramic are another solution to eliminate the discharge of current through the bearings. Non-conductive ceramic materials prevent shaft currents from flowing through the bearings and damaging the motor. Since no electrical current flows through the motor bearings, there is no chance of current-induced wear. However, the current will seek a path to ground, which means it will most likely travel through the driven equipment. Since ceramic bearings will not remove the current from the rotor, only specific applications such as direct drives or equipment utilizing non-conductive couplings are recommended for motors with ceramic bearings.
Okay, so I imagine everybody kind of got the general idea of that. So the way that this works is there are different types of bearings, and this actually right here is a insulated bearing. So the way that this works is the internal components, there's these in other ones that would be steel balls, but in this scenario these are filled with ceramic. So ceramic is very durable and it's non-conductive. So when you run electricity through ceramic, it's not going to do anything. But if I run electricity through metal or copper or anything like that, it's super conductive. So that's another thing you have to pay attention to. Is it can be even just the internal components that you're not paying attention to inside your motors. So your motors themselves, you have to pay attention to the internal components because there is a lot of harmonics in the lines. The Bitcoin mining fans themselves run at different frequencies just because of the way that they're operating. Every fan runs at a certain frequency. Usually that's around 50 to 60 hertz at max operating condition. With that though, if you have different frequencies in your lines as well, this is another common electric problem, is if you have different frequencies in your lines, that can actually converse to the electrical components in your system too. So you can have an effect where you're having, it's almost like not having a breaker on your system. So if all of your PDUs are connected to the same breaker and one PDU blows up, all of them are going to blow up. It's just going to be a cascading effect because there's nothing on that line to stop that. It's the same with your motors too. So if your motors, there's this thing called electromagnetic current filter. So there's certain frequency filters that you need to put in place so that this doesn't help happen, because what can happen is your internal components can start welding, and we'll get into that a little bit more when we start talking about the motors and the different motor efficiencies, the classifications for motor efficiencies, and the reliability aspects of them. But that's all I had for that video.
Austin, so I want everybody to now go to the next poll. The poll is, when will you likely purchase your next industrial fan or exhaust system? So just everybody can open up the activities section in the bottom right-hand side of Google Meet and answer that. So the options are next week, next month, next year, never, or not sure yet. I'm seeing a lot of people say not sure yet. That's fine. And one person said never. That's okay. Buying industrial fans might not be for you. That's okay. Maybe it's somebody else in your company, or maybe you're realizing Bitcoin mining isn't for you. Hopefully that's not the case. But I think as a Bitcoin miner, you're definitely going to be interested in what Austin has to say here, because getting that hot air out of your mine is one of the absolute most important things you could do, other than keep your power on. And keeping your place clean too, right? So yeah, just
Yeah.
go ahead. I'll wait for a couple more responses on that. When will you likely purchase your next industrial fan or exhaust system? We got 9 votes. Okay. All right, Austin.
All right.
Go
I'm
ahead.
gonna refresh this real quick. There we go. Okay, so we're gonna talk about like the different fans. So if you guys are gonna be looking out for fans, kind of learn the like what's it gonna look like for you. That's kind of like what we're gonna be painting an image. So there are certain fans, they say that they do 50,000, 60,000 CFM, and we're gonna hop into example, and I'm gonna pull a real world example from actually a company in Texas that I feel like a lot of people really get burned on. Just because they claim that they're an industrial fan, but it's actually a fan from Alibaba that's like $100, and then they just pretty much refabbed it. So that's what we're gonna kind of get into. Where an actual good costing fan is gonna be around, and it's gonna cost you a little bit more capital because it can do more for the different resistances in your Bitcoin mining system. And it's not just the fan that's very important. It's also the motor. It's also the van blade, the drive system, different torque efficiencies and whatnot. So if you look at the fan on the left, there's some heavy duty. I've seen, for example, some of the crypto container pods. I see these really heavy duty cabinet fans, and they have these giant tube axial, all they're called all weld aluminum blades. So they're all welded around the hub, and they're really good for static pressure, but they're extremely inefficient on the CFM side, where you're going to be using a 5 horsepower motor for 15,000 CFM. Where the other fan that's really bad is the plastic fan. So I see a lot of people buy like greenhouse fans or J&D fans, or things like a company Utilitech, it's Menards fans, any type of fan that's kind of like designed pretty much for residential use or just kind of light duty use. Those aren't going to last you very long just because of the way that it's designed. So as you know, in the Bitcoin miner, that is a plastic blade. So plastic blades don't usually last that long, just because what they do is they're not that heavy. So the inertia, the centrifugal force and inertia when it is spinning, it if that blade has mass, it's going to keep spinning on that bear. It's going to be a lot harder for opposing force to slow that blade down. But if I have a very light blade, it's almost like paper, where if you attach paper to hubs, that paper is not going to it's going to be very static affectant, if that makes sense. So your fan essentially loses output, it loses the velocity that it's going through, and it's also putting overamping your motor. So this is another common problem, is if your fan and motor are under a lot of static resistances, it's stressing out your motor, especially if you're using direct drive, because direct drive, you're putting all the torque in straight into the motor. There is no belts or anything absorbing that vibration and that torque. Whereas belt drive, you also have the kind of the different torque efficiencies with a pulley system, because pulleys are just engineer wise, well, the physics, I guess, behind them works a little bit better. And then we're going to talk about the velocity. So your really bad fans are going to have smaller horsepower motors. They're going to claim that they do like 50, 40, 50,000 CFM, but when you actually put them in the resistances of a Bitcoin mining, I guess, system, you're going to see CFM ranges down to 17,000 CFM. So if this, like for example, like these J&D fans, they might be rated at 50,000 CFM. I put them in my mining system that's almost directly aired outside, right? With just let's say we have 50 miners in that system, that fan is only going to be able to handle about 15,000. Whereas if I have a more heavy inertia blade that can handle different stack resistances, you're going to get that actual 50,000 or even more out of it. And that's what we're going to get into, is there's different curves and different things that you have to account for as well. So this is the part where we're going to be check and balance. So this is where you have to build the credibility of who you're buying fans from, and make sure that you're not just buying an aftermarket fan that's not designed for continuous use, because these things have to be reliable. They have to be running 24/7, 365. That's how Bitcoin mining works, and that's how you have to optimize your system for it to so that you get the most output on your ROI and your income. So I'm going to open up this tab first. This is a competitor. 1 second. I have to change the screen real quick. So this is this is the most common fan that I see engineered wrong, and it's not just the fan; it's actually the fan blade. So these fan blades actually come from China. They're extremely cheap. You can buy a whole casing for them too. That's what they actually come in, is they come in like a square casing. Extremely terrible fans. I highly do not recommend them, especially for Bitcoin mining. But what we're going to do is we're going to dissect the what they're faking out pretty much. So for example, this fan says 43,000 CFM. So we're going to view this fan and kind of dissect what it actually is going to be doing. So these guys claim that this fan does 43,000 CFM, and it's using a TFEC 1.5 horsepower motor. Now, if I look at this guy's fan specs, I don't know if you guys can see that or not, but on this bottom right here, you see how it says right on the distance from the fan, right? So if I'm at 0 distance from the fan, this is the measurement he's taking on the fan blade itself. So I use a measuring tool that tells me how fast the air is moving, and I can calibrate that by, well, I can find out the CFM by taking the diameter of that fan and reverse engineering this guy's fan specs. So if we look at his fan, it's doing at 0 feet right in front of the fan, it's doing 1,320 feet per minute. That's how fast the air is moving in terms of feet per minute. Now the airflow is mile per hour. It's 15 miles per hour. Now you're probably wondering, like, how do you reverse engineer that? How are those specs useful to me? Now, the thing is if you actually look and reverse engineer, which I'm going to change my screen real quick to a third-party calculator so that you're not going off of my specs. We're going to use a trustable source for this to calculate. All right. So this is a airflow calculator. This you can enter in certain inputs. And this one I like the most just because it's simple in terms of figuring out, like I can just enter in the radius of a fan rather than kind of calculating doing like pi times the r squared. You define the total area. So what you're trying to find is the airflow volume. So this guy claims that his fan is doing 43,000 CFM. And don't get lost. And what a lot of fan companies like to do is they actually like to confuse you with different specs. So they'll, instead of using CFM, they'll use like feet per minute, or even better, they'll even use metric measurements. So they'll use like millimeters per minute, or meters per minute, or meters per hour. So you have to also pay attention to the scale ratio too, and kind of know what your units are, because they'll kind of scam you on that as well. But if we were looking at that fan, it was a let me look back again. Yeah, it was a 59-inch fan. So in order to calculate the flow, or what the velocity is going to be on the back end of that fan, we're going to have to take the radius, which is the diameter divided by 2. So if I take a 59-inch fan divided by 2, I believe that's 29.5. So we'll throw that number in there. So, and then if I calculate the airflow, my Wi-Fi decides to work. Maybe. One sec, I want to refresh this.
And do you have some sort of ad blocker or JavaScript blocker on?
I might. Maybe. Are you fine with me just screen sharing this portion to see? It might be something in the background that's blocking it from loading.
Yeah, I mean, I can see your screen right now. But it's okay. I mean, you can fake the numbers for now and just tell us what your outcome was going to be.
Yeah, so what the actual outcome was is the fan actually did it does 21,000 CFM. If you actually look, so what will happen is if you enter in 43,000 and you enter in the radius, it'll tell you a number right here, the feet per minute, and it'll be way higher than what that guy was actually claiming it did. It'll be around like 16,000 feet per minute. But if you reverse engineer the flow, it'll show you. You can scale that down. So if you enter in 20, if you guys, I'll send you a link after this so you can credibilize, kind of take this and calculate it on your own. But what you'll see in the end is that there are certain specs and stuff that can be flawed or faked. Is this guy's going to claim that his fan can move air at 15 miles per hour, but it won't even get close to that. It'll be around like 10 or 9 miles per hour, and that all affect that, because the way that air works is there's certain equations and whatnot, and they work together to kind of it's kind of like a control variable equation where if you put an input number, you're going to get the same. It's going to be overlapping in a same a similar variable. It's kind of hard to explain without this calculator not working, but I guess we'll move on from there. All right. So we're going to talk about the different types of fans, and I feel like there's a lot of stuff that you can learn about this, because there's certain types of fans that offer higher static resistances, and there's some that are extremely inefficient, but they'll move air through a long amount of ductwork. So you have centrifugal, blower fans, mixed flow fans, upblast fans, and axial tube axial fans. And there's also You could call them vane axial, but they're pretty much the same as axial. Oops. So go centrifugal. So centrifugal, if you have one of these, you probably do not have the right airflow, just because these things use a ridiculous amount of energy just to get a little bit of air moved. But if you have, let's say, like 100 feet of ductwork that you have to move something through, these are amazing for that. These actually are very common for woodworking systems, and well, occasionally really desirable for woodworking systems, because what you can do is they create a lot of static pressure. So what you can do is you can suck up wood and metal shavings and whatnot with these, but you have to output a ton of power to get just a little bit of air moved, and that's why these are usually in much narrow ducts, so that they can it's almost like a hose. So if I take a hose and I put my thumb on a water hose, right, I'm not changing the output that's coming out. I'm just increasing the velocity it's coming out. And that's kind of the same scenario that you're running into with centrifugal fans. But I highly do not recommend optimizing for those. Mixed flow, they're actually pretty good. A lot of these, 90% of the time, they're mounted in a cabinet, or they'll be scaffolded up. If you look at Walmart, Sam's Club, that you actually see some of these maybe hanging up in their warehouse. They're actually used mostly for emergency smoke and exhaust ventilation systems, as well as fresh air. These are very quiet. Just the way that it moves the air. Its design is actually very unique. So it mixes cold air with the inline air around it. So it kind of dissipates its own pressure in a very unique way. These, I'd say I would stay away from them to a certain extent, just because they can use a lot more energy from what you would get in an axial fan. But if you're worried about sound quality, you might want to optimize for these. Or if you're moving air in a tubular ductwork that's very long, then this is what you're going to optimize for. But there is, we're going to get next to the tube axial. I think that's the better option if you're going to be moving air through a much longer ductwork. Just because the way that these are designed is you're going to get the most air movement for energy out of a axial fan. And these are probably the most common, but you have to be very careful, especially when it comes to the fan blade design, the motor that's behind it, the bearings behind it, because all those components are they're pretty much liabilities for your HVAC system and your infrastructure. And you can have unintended downtime if you don't engineer it right right off the bat, because you can run into problems with static and whatnot. And these things are the least static resistant fans. So that's what the trade-off is you can optimize for the centrifugal or the mixed flow, but you're not going to get the efficiencies, and you're not going to well, you're not going to get the efficiencies. And if you optimize for the tube axial or the axial, you're going to get more efficiencies on moving less resistance air. So when you're designing your system, that's what you want to keep in mind when running these fans, is make sure that you take all the stress that you can off your system, because these fans become more efficient. But we'll move past these and we'll talk about the upblast application. I honestly think that the upblast application is one of the best applications. It can be variable though. So the upblast costs a lot more because you have what's called a roof curb, and you have all these different adapters, and then you have to have roofers kind of put in that rubber. There's a rubber membrane. Most of the times, there's rubber membrane on top of your ceiling if you're in an industrial environment. So you have a lot of patching. I think it's like $2,000 per curb just to have a roofer rubber seal it. So if that's your main concern is capital cost, I would stay away from upblast. Not unless you can get like a really good deal on like short upblast, because short upblasts are pretty cheap. You're minimizing your expenses in material cost, because these things are pretty big. They're it's called a wind band on top. 90% of the times, that's what they have. They'll call it a vane axial. Or a vane section. What these essentially do is they just protect the hot air that's being exhausted out of your fan. It creates a chute for it, kind of like a vortex chute, so that when there's air or wind that blows past those fans, it at least has some time to build up its static pressure and its velocity in a vortex motion going up into the atmosphere. So it holds that hot air up in the atmosphere opposed to holding it lower down to the atmosphere. And
Yeah.
that's where a lot of problems happen. Is I'll see people, they'll run these fans right off the roof, and they'll be panel fans, but then the velocities aren't high enough, and it'll go right back down to their intake. And there's a lot of different environmental aspects too that we're going to get into that affect this, like where gravity can actually push the hot air closer to your elevation, and it can create that problem where you're cycling your own heat from the little bubble hot air atmosphere that you're creating around you, and you're just cycling it back down into your intake system. That's no good.
Awesome. Austin, yeah, we're gonna open it up for questions and answers here in the next couple minutes, but if you just want to finish up your last one or two slides, then I just want to let everybody know, be ready to turn your microphones back on soon and your cameras back on. We'll give Austin another 30 seconds to 60 seconds just to finish up his last slide here, and then we'll do that.